Hey guys, Mr. Wemp here, and we are today looking at truth tables and the logic expressions that I can then get from a truth table. So basically, we're going to be looking at a binary truth table and then looking at the expressions that would come out of that truth table. And the truth table is really one of the first things that you do when creating a equation for what your problem is going to be doing. So we're going to look at how to properly construct a truth table right there. We're going to learn how to write a sum of products, SOP, the sum of products logic expression from a truth table. We're going to create a truth table with a sum of products expression, so we can create a truth table from the expression, and we're going to create an expression from the truth table. We can get both of those. And we're going to also create a truth table from a set of design specifications, so that would be a word problem. Okay, you guys are used to word problems, so we'll take a look at one of those as well. All right, so how do we construct a truth table? Basically, when we look at a truth table, we have 3 or 4 sections to look at. First of all is our output. That's going to be known as our function. Okay, so the function F1 is one of our outputs. In the breadboard companion, that would be one of the lights. Our inputs, these are where we're getting our inputs from. So in our AOI logic, we would look at X, Y, and Z as our switches, or our inputs, or our keys in the door, the seat belt, whatever is causing a 1 or a 0, whatever your action is, those are going to be up here under your inputs. Okay, the more inputs you have, the higher your binary count and the larger your truth table is. With just 2 inputs, it's a very simple truth table. 3 inputs, it gets exponentially bigger. And then we have, of course, our input combinations. These are all the different combinations, and we just look at it in a binary count. So we have this one can go up to 1, 1, 1, but in a binary count we have 0, 1, 0, 1, 0, 1. You can actually build these pretty easily. Okay, so we have 8 combinations with 3 inputs. 2 inputs has, I believe, 4 combinations. 1 input has 2 combinations, so 2, 4, 8, 16, 32 combinations, just like binary does. Okay. Over here we have our outputs over here on the right hand side, and our outputs for each input combination. So what does that mean? That means that in this particular situation with a 0, 0, 0, my output would be a 0. In this particular situation, a 0, 0, 1, my output would be a function of 1. All right, so basically we just fill this out in a binary count, and our function is either the equation or the equation is the function. Okay, so let's take a look at some examples. We have a 2 input, we have a 3 input, and we have a 4 input. And with the 4 input, you can see that this is, let me move this out of the way. You can see this is quite a bit larger than the 3 input. Generally, we don't mess with anything bigger than a 3 input. But for our project right now with the voting machine, we have a president, vice president, secretary, and treasurer. So we'll have a fairly large truth table. On a large truth table, you end up with more functions. And with that, that's going to lead us into what we call the Boolean algebra. And with the Boolean algebra, that's where we're going to simplify this, because you can see there's quite a few ones over here. Each time you have a 1, you get an equation. Okay, and we're going to do the sum of products. So you have this plus this plus this plus this plus this plus this plus this will all give me a function. Okay, so let's take a logic expression from a truth table. This is pretty straightforward. I just want to look wherever I have a 1 for my function on the truth table. I'm going to look there, and that is going to be my equation. So in this one I have X, Y, and Z is a 0. Z would be anything. If it's a 0, it's a naught. So it's not Z, it's Z naught. So we have this guy here, this guy here. Whoops, that was a mistake. We probably don't want that one. Guess I can't erase it, so we'll just cross that out. X naught, Y, Z, and X naught, Y naught, Z. So all of these looks like 1, 2, 3, 4 different min terms. Those are called a min term. Those little min terms, when you sum all those together, this is a product, they're multiplied, but if you sum them all together, you'll get your functions for f5. So that's your possibilities. So I just take x naught y naught z plus x naught y z plus x y naught z naught plus x y z naught. When I sum those all up, I get my function at 5, or my fifth function. And basically this would be an OR gate. So we have OR. Oops. Let me write that in there. Then we have OR. This is x naught and these are x naught and y naught and z. So it has to be x naught and y naught and z in order to get a function. So where do I see that? X naught and y naught and z. So that would give me a function. Okay, that leads us into the next part where we would actually pull a truth table from the expression. But let's take a look at this one. What do we have for our function? We don't have all that much. There's that one, that one, that one, that one, and that one. So let's go ahead and write a logic expression and see what we get. From this guy we have, this is a naught, b naught, c naught, d. So a naught, b naught, c naught, d. Notice that they're not in one big bar. Over here we have a naught, b naught, c, and d. So we have a naught, b naught, c, d. The next one down we have a, b naught, c, and d. So we have a, b naught, c, and d. Then we have a, b, c naught, d, and a, b, c, d. Okay, so again, anytime it's a 0, that would be that output or that input naughted. So these 5 terms will all be summed together to get my function. So f6 is equal to a naught, b naught, c naught, d, or a naught, b naught, c, d, or a, b naught, c, d, or, and we just kind of keep going through. And I just moved that down. It's a big long equation. And the final one is a, b, c, d. Okay, so this is my function from this truth table. And there it is, nice and neat, so you can see that. Okay, so let's create a truth table from the following expression. So we can also create a truth table based on what our expression says. So in this one I have 3 inputs, but you see it's x naught, y naught, z naught, and then I have x, z. So I don't have 3 terms in all of these. So basically we're going to look at our expression and find all the things that will allow us to create a truth table. So in this example here, if I go back one, my truth table clearly has 4 inputs. So I have A, B, C, and D. And you would create this big table. We have a function. And we just have 0, 0, 0, 0, 0, 0, 0, 1, so on and so on and so on. And what I would do is I'd find where it says A, B naught, C, D. Well, that's going to look like, so I'd have A, B naught, C, and D. My function there would be a 1. All right, so that's pretty easy to find that one. But what about this guy over here where I have A naught, B naught? Well, it turns out in this particular situation, A naught, B naught, when I have A naught, B naught, it's referring to just those two, and I really don't care what C and D is. So I'm not even going to look at C and D. I'm only going to find where A naught and B naught meet that criteria. So if I have A naught and B naught right there, I really don't care what C and D is, so that's a 1. I still have A naught and B naught here. I don't care what C and D is, so that's a 1. And I would just keep going through, and you do that for each one of these. And eventually what you end up with is a truth table that looks like this. All right? So if the truth table looks like this, basically A naught, B naught is these 4 min terms, or these 4 functions, And then we start adding these in, and you end up with having a truth table based on what your function was. Okay, now a lot of times you'll actually go the other way, but this will work in this direction as well. Okay, now let's look at some design specs. So here's an example of some design specs and a truth table trying to figure it out. So we have a large fuel tank that has sensors that monitor temperature and pressure. Both sensors output a logic low so we have a logic low or 0 if they are within safety range. So an alarm will sound if either sensor indicates an unsafe condition is present. So we need to create a truth table for this logic design. So we're gonna assign some inputs here. So we have a pressure sensor, a temperature sensor, and an alarm. If the pressure sensor is a 0, it's safe. If it's 1, it's unsafe. If the temperature sensor is 0, it's safe. And the alarm, if it's a 0, it's turned off. Okay, so we get that from our design specs. And our truth table says that an alarm will sound if either sensor indicates an unsafe condition. So if P or T are 1, we don't care which one, it's if any of them are unsafe, which is here, here, and here. If any of those are within range, we get an alarm. So there's our alarm, there's our alarm, and there's our alarm. So our alarm is our function, and these are our inputs. So we have 2 inputs and a function. Anytime, and now notice here that they're both unsafe. All I care about is either. So I don't care that they're both unsafe. I care that one or the other has gone off. So that gives me my alarm. So from a word problem, I can also create a truth table. Once I create my truth table, then I can get my expression, which is my function or the alarm is equal to P naught T or P T naught or PT. So those would be my 3 expressions that I would get. Okay, so let's look at one right here. I'm going to go ahead and let you work this one out, and then we'll look at the answer in just a moment. So go ahead and pause the video right now, and then come back to it after you've worked out this problem. Okay, so we're back now. Let's go ahead and take a look at this problem and just see how you did. So your teacher keeps final exams in the office. For security reasons, you need to design an alarm system for the office. The office has a window and door. So let's write down some of what we know. We know that there's a window, there's a door, okay, and they're equipped with sensors that output a 1 when they are secure. So closed equals a 1, and open equals a 0 on both of them. So closed equals a 1 and open equals a 0. All right, so there's that one, there's that one. When the alarm system is turned on with a key, a siren should sound if either the window or door is unsecured. So now we have a key, and I can't remember. The key may be a part. So let's see. Where's my alarm? And the alarm. Okay. So we've got those 3 or those 4 components. Now let's see what this would look like. So we have a key. If the system's off, anytime that the key is a 0, is there an output? No, there's not going to be an output. So we look at key, and anytime the key is a 0, we get an output of 0. So that automatically, since that overrides everything, those are my sirens. Okay. Now, if the key is on, which is down here, now we can look at the door and the window. If the door is open and the window is open, or let's see, the door or the window is open, I'm going to get an alarm. So they're both open there. So there's a function. One's open here. The door is open. So there's a function. Here the window is open. So there's a function. And in this one, the key is on, but the door is closed and the window is closed, so we don't get a siren. So these 3 scenarios will provide me with a siren. So what does that look like? So we have, so my siren is equal to, if we put this in sum of products, we have K D naught W naught, or K D naught W, or K D W naught. So that's my expression that would give me a siren. That would give me a functional function or an output. Okay, so that is basically how you get your design specs, or you get a truth table from either the expression, or you get an expression from a truth table, or from your design specs. So it's a pretty straightforward system. It's going to be key, though, that you know how to do that. So we'll let you practice on the sheet, and good luck.